There are some Lewis structures that just don't seem to work using our old way of doing things. The best two examples I can think of are these two here, PCl5 and SCl4. It's quite obvious with PCl5, something's going to go wrong. How can we have 5 chlorines attached to something that's going to obviously break the octet rule? You're going to have 2, 4, 6, 8, 10 electrons around the phosphorus for that to happen. We can't bond a chlorine to a chlorine because it only has a valency of 1. So what's going on there? What we find is that some elements, when they're the central atom, so when they're the central atom, this is when it works, are able to break the octet rule. And this is where our understanding of atomic structure, the electron configurations, really helps us. So phosphorus is one of those examples that can break the octet rule. And the reason for that is it's got electrons in the 3s and 3p orbital, but nothing in the 3d. And what it can do is it can actually promote one of those electrons from 3s up to 3d to give it 1, 2, 3, 4, 5, a valency of 5. Each of these electrons can be paired to create a bond. So it pairs with an electron from chlorine, and in doing so creates those 5 covalent bonds. Now I still wouldn't need to check. Now phosphorus has got 5 valence electrons, and each chlorine has got 7, so 35. So in total we need to have 40 electrons. Let's double check if we've got that. Now there's 5 chlorines. If we add up what's around one of those, we can times it by 5. So 2 for the bonding, and then 2, 4, 6 lone pairs, so 6 plus 2, that's got 8. Each of those has got the same arrangement, so 5 times 8 is 40. We've got 40 electrons. This works. But it has broken the octet rule for the central atom only. Now sulfur is an interesting one. Sulfur has a valency of 2. It's straight under oxygen, so you'd expect that. It's got 6 valence electrons. So how can it bond to 4 chlorines if its valency is only 2? Well, this is the same sort of thing. It's got electrons in the 3s and the 3p, but it doesn't have electrons in the 3d, so it can actually promote an electron up there. And in doing so, its valency goes up to 4. Now, sulfur's a really funny one. It can do some really tricky things. It could also promote this electron up to create a valency of 6. So sulfur can have a valency of 2 with its electron arrangement as it normally is, 4 when it promotes 1 from the 3p, or 6 when it promotes 1 from the 3p and 1 from the 3s. So it's a really, really tricky example, and one that we need to work out. So here's how I would construct sulfur. First of all, and I haven't finished this one here on purpose, I put my sulfur in the middle because it's got the highest valency. Chlorine's only got a valency of 1. So I put my sulfur in the middle. Then what I do is I put each chlorine around it and give them a bonding pair of electrons. That uses up 2, 4, 6, 8 of my 34 electrons. I then use lone pairs to make each chlorine obey the octet rule. Because it's on the outside, it's not the central atom, it's one of the ones on the outside, it's going to have to obey the octet rule. So therefore, I add up all my electrons and I get to 32. 32 is not enough. So I've got 2 more electrons to go. Well, and I'm going to move my camera here, sorry. Actually, that's shown here as to what's happened. This one's moved up to here to give us our 4 bonding electrons. And that's our 4 chemical bonds there. But there's still these 2 here, and they're still technically part of the valence shell. They're all on the 3rd energy level. So I need to represent those 2 as a lone pair. So I put 2 more anywhere here, but they have to be paired. I can't put 1 there and 1 there. They have to be paired up, and that represents my lone pair here. So hopefully you can start seeing the link now between Lewis structures and our electron configurations that we did earlier in the topic. The best way to learn these is just do lots of practice of them, and the SciPad has got a lot of them, and I've put some in our in our notes section of our Microsoft Teams, which have got some that obey the octet rule and some that have expanded octet rule. So lots and lots of practice is how we get good at these ones here. We still use the same rules as we did before to create our Lewis diagrams, but we need to be aware that sometimes that central atom, only the central atom in these ones, can break the octet rule, and here is our reason why. It's to do with moving electrons into the 3D orbitals.